And I don't want to dwell on these examples of electronics because you're familiar with them. But I mean, look, here's a good example, the price of a transistor. When I was a high school student, I used to hang out at the surplus electronic shops on Canal Street in New York and buy something this big, which was a telephone relay that could switch one bit for $50. 1968, when I was a college student, I could buy a transistor that did the same thing for $1. 2002, I could buy 10 million for $1. Today, you can buy 300 million for $1. So you've heard these fantastic comparisons, but again, look at how smooth a trajectory this. Look at how predictable a progression this is. And this, again, is the measure of the innovation of millions of people around the world. And as we've made them cheaper, they're actually better because they're smaller. The electrons have less distance to travel, so we've had exponential growth in the speed. The cost of a transistor cycle has come down by half every year. That's 50% deflation. And we see that in every example of information technology. Sequencing a base pair of DNA, that was $10 in 1990. It's a small fraction of a penny today. All these different measures of cost of what it takes to perform some digital function comes down by half every year. That's 50% deflation. And the economists worry about deflation. We had massive deflation during the American Depression in the 1930s. And the concern is, as everything becomes information technology, Ian mentioned printing out three-dimensional objects, by the 2020s we really will be able to print out just about everything we need as very intricate three-dimensional products from desktop factories, from information files. Everything is going to become information, and if that has a 50% deflation rate, the size of the economy, this is the concern, will shrink. Because people aren't going to actually double their consumption every year to keep up with this 50% deflation rate and actually buy twice as much stuff, so therefore the economy will shrink as measured in constant currency. But actually, that's not what we see. We actually more than double our consumption every year. We've had 18% growth in constant currency every year for the last 50 years in every form of information technology, despite the fact you can get twice as much of it every year for the same cost. And the reason for that is as price performance reaches certain levels, whole new applications explode on the landscape. People didn't buy iPods for $10,000, which is what it would have cost 15 years ago. So whole new applications just explode when the price performance reaches certain levels. And the biotechnology revolution, I mentioned, that's revolutionizing our health. Again, smooth, exponential decline in the cost from $10 in 1990, small fraction of a penny today. The first genome cost $1 billion. National Institutes of Health in the United States is collecting 1 million genomes now for $1 billion. This slope on this curve, on this logarithmic curve, represents a smooth doubling every year, the amount of genetic data we've sequenced. And this applies to every other aspect of our biology. Communication technology, which I mentioned is very democratizing, is doubling every year. There's many different ways to measure this. Here's that curve I had of the internet, and I had a little piece of this in the 1980s, and I projected this continuing. If we look at the same data on a linear graph, it looks like this. This is the same data, but on a linear scale. And so it looked like the World Wide Web came out of nowhere in the mid-1990s. But if you looked at the exponential progression, you could see it coming. We're shrinking technology at an exponential rate, a factor of 100 per 3D volume per decade. So these technologies will be 100,000 times smaller than they are today in 20 years, by the late 2020s. If I were to say that someday you will have millions or billions of blood cell-sized robots in your bloodstream going through and keeping you healthy at the cellular level, you'd think that's very futuristic. But there's already 50 experiments of doing that with the first generation of devices in animal experiments. One scientist cured type 1 diabetes in rats with a blood cell-sized device that lets insulin out in a controlled fashion through 7-nanometer pores. At MIT, they have a device that's blood cell size. It goes in the bloodstream, finds cancer cells based on the antigens on their surface, latches onto the cell and destroys it. This is a design of a robotic red blood cell that is designed on the West Coast, and that it's basically a robotic version of your red blood cells. And it brings up an interesting observation about biology. Whereas biology is very intricate, it's also very suboptimal compared to what we ultimately can engineer with nanotechnology. And a conservative analysis of these resporocytes, robotic red blood cells, indicates if you were to replace a portion of your red blood cells with these robotic versions, you could do an Olympic sprint for 15 minutes without taking a breath, or sit at the bottom of your pool for 4 hours. And this is ultimately will be true of all the different systems in our body. There's not a single organ in our body that's not already being augmented or redesigned at some level of expertise. If you go out 20 years, we're going to be augmenting and replacing our biological bodies with systems that are far superior. So as we go out to the 21st century, we'll have plenty of computation at very low cost to do things like simulate the human brain. But then the issue is, will we have the software? And this has been controversial. Doug Hofstadter said that, well, perhaps our brain is just below that level necessary to understand our brain. And if we were smarter and able to understand our brain, well, then necessarily our brain would have to be that much more complicated and we'd never catch up with it. Maybe there's a math theorem in there that a complex system like the brain can't be so complex as to understand its own complexity. But it turns out that's not the case. We've already simulated many different regions of the brain. The amount of, as I mentioned, the amount of data we're getting is doubling every year. The spatial resolution of brain scanning in vivo is doubling every year. And we are turning this data into working models and simulations. This is a block diagram of a dozen regions of the auditory cortex that have been modeled and simulated, and sophisticated psychoacoustic tests applied to the simulation. They get very similar results. There's a model and simulation of the visual cortex, which similarly has been tested. There's a model and simulation of the cerebellum, which is where we do our skill formation, like catching a fly ball. We always wondered, how does a 10-year-old kid catch a fly ball? I mean, all she has to do is solve a dozen simultaneous differential equations in a few seconds, and most 10-year-old kids haven't taken calculus. So how does she do that? Well, we actually understand now how that works. Those differential equations actually are solved by the cerebellum subconsciously. You have to train it, which is why you need to practice the skill. And we have simulations of the cerebellum, which work very similarly to the human neural cerebellum, and these have also been undergone sophisticated tests. There's a simulation of the cerebral cortex, at least a substantial slice of it, being undertaken on an IBM supercomputer, which has already been tested for certain things. It's in an early stage, but that's arguably the most important region. I make the case in Chapter 4 of Singularities Near that we will have very detailed simulations of all the regions of the brain within 20 years. That will give us more insight into ourselves, which has been the goal of the arts and sciences for millennia. We'll have better means of fixing the brain, and we'll have better models, algorithms, methods to apply to these very important computers to create more intelligent artificial intelligence.